So just as a recap, the stability part is proportional to binding energy per nucleon, right?
Yes.
So more the binding energy per nucleon, more will be the stability. So what is the binding energy? Delta m c square. What is delta m?
Difference between mass of all of the individual number of protons and neutrons and the mass of the nucleus as a whole.
Correct. So if we have any nuclear reaction, which is A plus capital A results into B plus capital B, where A and B are particle, A and B are nuclei. Then in a chemical reaction, okay, when we talk about binding energy of a nucleus, okay, no, this is something different. So, okay, we are talking about the X. So delta M will be how much? What is delta M here? How to write it? If this is your atomic nuclei,
Sure, we can write it as E is
That is-
our atomic number. So it will be A
yeah,
into
it is-
mass of proton.
okay, huh?
Sorry, Z into mass of proton plus A minus Z
Mhm,
into mass of neutron
mhm.
minus Z into mass of electron, I guess.
Mass of the nucleus, right?
Yes.
Mass of the atom minus,
Into mass of electron.
so this is the atom, right? Mass of atom minus plus,
Yes.
become plus. So I can write is so this is the nucleus which is formed, and this is the constituent nucleons which is forming it. So the difference is called excess mass, right?
Yes.
So generally, how we write it? So mass of proton is never written in any question when you solve in the examination. They will never give you mass of proton. Rather, they will give you mass of hydrogen atom. So the protium, we call it protium. We have three isotopes of hydrogen: protium, deuterium, and tritium, tritium, whatever you can say. So the way of writing is mass of proton minus. Okay. So this is the conversion factor. If you want to replace a proton, this is a way to replace, and in every question they will give you this mass always. So this is question 1, this is question 2. Can we substitute the question 1 and 2? Now, if you substitute from 1 and 2, what is the delta now? Z into mass of hydrogen element atom plus A minus Z. Now, mass of neutron they will give you, so no need to worry. Minus now, do you see the benefit? Something nice will happen. What do you see here?
Mass of electron gets
Gets cancelled. So this way of writing is preferred because Now we are not supposed to write the mass of electron separately because it will be taken care by the H atom. So so the excess mass now turns out to be how much? Z into mass of H atom minus, what is that? Plus A minus Z minus mass of. So now, given the atomic mass of the nucleus, so in this way of writing, we get rid of mass of electrons. So there's no need to write because the mass of electron in this and in this will cancel each other effect, and then now this is the simplified way of writing it. And that is why, I mean, this is a very illegal agenda in nuclear physics, that they always want to express the mass of proton in terms of mass of H atom. I hope this is clear.
Yes.
So they will give you this mass, they will give you neutron mass, they will give you the atom mass, and from there you can find the excess mass. I think this is not very difficult. So binding energy will be how much? So binding energy will be given by the Einstein mass energy relation. So the loss in mass. So when you form
This
at
is
nucleus from this constituent, this is the mass lost into C square. Okay. Now what you need to remember that one unified mass unit. I hope you know the unified mass unit. What is one unified mass unit? 1/12 of
1/12 of the mass of a carbon.
mass of carbon 12. I hope you remember this.
Yes.
Yes.
And how much is this in kilogram? So in kilogram it is this how much? Tell me. So okay, we need to know the exact value. So we need to look for the value. So if this much one unit converts into pure form of energy, if you convert this much energy into energy, so binding energy for one unified mass unit is how much? That's the question. So we roughly remember that this value is equivalent of because how to write mass in terms of energy? So if energy is mass into C square, so mass will be energy upon C square, right?
Yes.
So one atomic mass unit is equivalent of 931.5 mega electron volt upon C square. This is the energy conversion which you are supposed to remember because you're not supposed to do the calculation of the same thing. Okay. I hope this is clear to all of you.
Yes.
So this value you are supposed to remember that how to convert because we are going to calculate delta M in some value. Okay. Some value of U. So once you know delta M in terms of U, multiplying this number with this value will give you the answer in mega electron volt. So this is how we express the energy. So binding energy is, I think, pretty simple how to calculate. If you want, you can calculate. Let me give you some numerical value so that you can do this calculation. I just wanted to show you the exact calculation. Some problems. Because these are values which we can't remember, we have to write it down. It will be given to you in the calculation. You can open SC Verma. I think I will just check the notes. Yeah. Okay, so values that you should remember. 1U is equivalent of 1 point, not equivalent, equals to 1.66054 into 10 power minus 2. So we need to know the exact value instead of approximate value, because the changes will be there only. Okay. And if you convert this into and the speed of light, we have to take as exact. And 1 mega electron volt is how much joule? So it is 1.60218. We have to make it everything very accurate, because 1.6 we know the answer, but now we need to know up to 5th place of decimal into 13, right? Joules. And if you do the calculation now using the formula, so 1.66054. Okay. Up to decimal 5 place is sufficient. And this MC square will give you answer in joule, right? So you can write as, if we want to express the answer in terms of mega electron volt, so how to write? Upon joule per MeV. So if you solve, this will give you exactly what I wrote. This is the answer. Okay. So this is the answer that you should know. So let's say if we have a, what is this? So in examination, they give that entire table of the mass. So we need not to worry about these values. But I can't remember these values. For me also it's difficult. So mass of neutron we write as 1.008 665 U. In terms of U, this is the way we write. So you can see the accuracy we need to write, okay? Because these things are generally ignored, but now you know why this is so much important. Einstein mass energy relation. And mass of H atom is 1.0. See, everything is 1, but now you realize that, okay, this is not exactly 1. And do you remember I told you that, okay, the neutron is made of 2 down quark and 1 up quark,
Yes.
but
Yes, sir.
the proton is made of 2 up quark. And I have told you that the up quarks are lighter than the down quarks, and now you can see the difference here. So after the third place of decimal, the difference is visible, but normally we don't take into consideration. Okay. So let's calculate that. So I'm looking for the binding energy for. So what is the binding energy for the H atom? Binding energy for H atom?
0.
No, why
Right.
0? H atom. How it is 0?
Electron to the nucleus.
So for H atom, this is the entire mass given, right? And what is the mass of proton? Mass of proton is not. Mass of H atom is 0. Now we can find the mass of deuterium. Yeah. H is something fundamental. So for H atom, we know the total energy. We don't know the. Let's find the mass. This binding energy of deuterium. So just to get the idea, like how to do the calculation, binding energy of deuterium. So deuterium is this, right? So how to delta M now? This is easy to write. So we have mass of proton plus mass of neutron in deuterium minus mass of electron, correct? Minus mass of deuterium. Am I right? But these two we cannot test. I hope you remember this. Mass of hydrogen, correct? Minus mass of electron, minus plus. So, oh, sorry, we have to add plus only. Yeah, all mass. And this we can write as this will gets cancelled out. Okay. Okay, why I wrote this, I don't know. And this gets cancelled because we don't want to write in terms of mass of electron. Now, I need to give you the mass of H atom, which is 1.0025. The mass of neutron is given 1 point, and mass of deuterium is known to us. So mass of deuterium is 2.014102. So these values will be given to you. So fine. And someone can do the calculation with a calculator and tell me the answer. How much is the answer? Tell me, guys. How much is the answer?
Yes.
0.002388.
0.002388, right?
Yes.
Very good.
Yes.
So binding energy of deuterium will be how much? No need to do the calculation, right? 0.00238 into 931.5 mega electron. That's it. Now do this calculation. Tell me the answer. How much is coming?
Sir, 2.224422.
2.224
422.
like this.
4422.
Yeah, I can double for that. Okay. This much.
Yes.
Okay, so you can see that binding energy of deuterium is how much? It is 2.224. Roughly, just keep it 2.224 mega electron volt. Now, do you realize the binding energy of deuterium is much more than the ionization energy? What is the ionization energy of H atom? Ionization energy?
13.6
3.6 EV.
EV, and this is mega.
mega.
It means no atomic transition can affect the nucleus because that energy will never come into picture, isn't it?
Yes, sir.
So in the process of excitation, de-excitation, or ionization, our nucleus will be unaffected. It will remain stable. Because to break the nucleus, how much energy we need to give? To break the nuclei, we need to give how much energy? 2.224 mega electron volt. Now, is it easy? The answer is no. It's extremely difficult. Why? Because this much energy should reach the individual nucleus. So the Large Hadron Collider, LHC, is meant for the same. There we create energy of a particle which colliding up to the order of tera electron volt. So now TeV, they are going to create now. So I think GeV is already achieved. The next 2029 reaction that will take place in the LHC, the world will change forever. So let's hope something great will happen. Okay, my purpose is to just show you that things like this is also there. Okay. Next. So we can go to the now. Q value. Okay. So what is Q value now? So Q value is meant for the nuclear reaction. Okay. So we define for it is defined as the total kinetic energy available to the products during any nuclear reaction. So what does it mean? Let's try to understand. So let's say a particle A is bombarded to a nucleus capital A. So maybe you can think of a Rutherford alpha scattering experiment in which the alpha particle is bombarded to the nucleus. You can think of one of them. Take one alpha as A, one nucleus as capital A. And after this reaction will take place, so we always get a meta state. So meta state is the unstable state of nuclei. Okay. So what is this unstable state? So you might have seen that in cricket match, sometime bowler will take the, the fielder will catch the ball, but if the But sometimes if the fielder is not in the right position, after even taking the ball, he will throw back the ball because he is going beyond the boundary line. Correct? So when you bombard the, let's say, alpha particle to the nucleus, first the particle will be absorbed by the nucleus. So you create a meta state, and the moment you absorb, the entire nucleus will become unstable, and as a result, this will break. Now this meta state persists for very, very small time interval. Sometimes it is impossible to observe also. And then it breaks into a new particle, new nucleus, you can say Bn, so with some release of some new particle B. So maybe some neutrons are released, if you remember the chain reaction, right, in nuclear physics. So every particle will have some rest mass. Let's say the rest mass of A is Ma. This is M capital A. This is M capital B. This is M small. So what is the energy? The rest mass energy will be how much? Ma C square. C square. Now, in most of the spontaneous reaction, if the reaction is spontaneous, it means the entire reactant will go to low energy configuration or high energy configuration. Which energy? Tell me. What is spontaneous reaction? What is the correct criteria? When we go from here to here, we must lose mass, isn't it?
Yeah.
So most of the spontaneous nuclear reaction will occur in a way to reduce the rest mass, not the mass. We talk about the rest mass, and therefore the Q value is called the total energy available. So when you convert from here to here, so you had energy this much. No. You had energy this much. Now you have energy only this much. So the obvious question is where the energy has gone now. So you had more energy, now you have less energy. So where that energy will go? Tell me. Can we say this energy will become heat energy? Yes or no? Imagine it is happening in the perfect vacuum. So can we talk about the heat energy in perfect vacuum? Tell me yes or no.
Sir, if it's being
Yes.
radiated, then probably.
No, I'm saying these experiments are performed in isolation in vacuum. So you have only one particle of A, one particle of capital A, and then B and B is formed. Can we talk about the heat energy? Yes or no?
Yes, sir.
I don't know, sir.
The answer is there is no question of heat if there is no medium.
Sir,
Heat is
but it
defined
can
for the
radiate.
medium. No? Heat is defined for?
What, sir?
Heat is only defined for medium. So without medium,
Achha.
how we can have heat?
We cannot.
This is just a isolated reaction. Just we have particles. Okay. And these
Yes,
are nuclear reaction, not the regular reaction, not chemical reaction, where we have the 1 mole of first gas, 2 mole of second gas reacting to produce 2 mole of third gas and something and so on. So in the chemical reaction, do reaction occur at a individual level, like the reaction is carried out with one gas molecule, or say like a large amount of molecules are there? What you see?
large amount.
So it means you create a medium, isn't it?
Yes, sir.
So generally you carry out the reaction in a liquid phase or a gaseous phase actually. So reactions are always having phase defined. Every chemical reaction will have phase, yes or no? Chemical reaction will have phase, yes or no? how you carry out the chemical reaction in some phase, no? Some liquid phase, some gaseous phase,
Yeah.
some powdered form, can say solid phase. But we are talking about the nuclear reaction, and here we are talking about the so Q value is the individual calculation which we make with the assumption that these are completely happening in isolation. So there is no one to take energy from here to convert it into some other form. So what will happen? This energy which is now available will become the kinetic energy of the new particles formed. So what particles we have formed here? B and B. So if there is no radiation involved in any nuclear reaction, then we say kinetic energy of capital B plus kinetic energy of small b must be equal to what? Understood?
Yes.
Now, here we have to again understand something more. The Q can be positive, Q can be negative also. Q can be positive and Q can be
Yes.
negative also. The question is, can we have the negative kinetic energy?
No.
No. So this assumption only when
Q
Q
greater
is
than.
positive. But there is some situation in which Q can be negative. So anyway, I'll come to that in detail. So Q, a positive value of Q is called exoergic reaction. Ergic. You have heard about thermic, right?
Yes.
Endothermic, exothermic, but that we use for chemical reaction. And there we talk about the heat energy, right? Here we don't talk about the heat energy, so we don't use the word thermic. What we use? Ergic means some energy is getting emitted, so which is not heat, so we say ergic. And Q negative is called
Endoergic.
endoergic. So as we proceed, I'll tell you that how these questions are brought into picture one by one. Okay. So we'll talk about the radioactivity. What is radioactivity, guys?
The first order reaction.
Stable nucleus.
No, don't give me the mathematical name. What is radioactivity as a phenomenon?
Decay of an unstable nucleus to form a stable nucleus.
Relatively formal, relatively stable, not absolutely stable, right?
Relatively stable.
Yeah, we cannot say that the stability will be permanent. It can further decay and make some even more stable
Yes.
nuclei. So we say relatively stable. So what is radioactivity as a definition? How you will define it?
The spontaneous change of nucleus into a more stable nucleus by emission of alpha, beta, gamma particles.
Alpha is particle, beta is particle, gamma is radiation.
Rays.
So we simply say radiation, right? Rays, alpha, beta, gamma rays. Yeah. Okay. So it is the spontaneous emission of particle due to the disintegration of unstable nuclei into relatively stable nuclei. That's simple.
Yes.
And this is spontaneous, which means
No external energy needs to be provided.
yeah, so no external stimulus is required. It happens on its own. So the spontaneous emission, of radiation the spontaneous emission of radiation due to disintegration of what? Unstable nuclei into what?
More stable nucleus.
Relatively stable nuclei, right? Is called radioactivity. So that name is radio means radiation and activity means difference. Okay, so we'll come to radioactivity later on. Right now we are going to study about the Q value, mostly Q value and its relation. Okay. So we'll talk about first of all alpha decay. So when alpha decay happens, first of all we need to know when alpha decay will happen. So alpha decay happens in a large size of nucleus, right? So
Yeah.
when it happens in a large size. So when N/P ratio exceed
1.5.
1.5. For heavier nuclei, the N/P ratio is 1.5. So if it is more than that, then alpha decay will happen. In this case, what will happen? A part of the nucleus will be, broken down, and you will get a relatively small nuclei. And what is happening? The large size is the problem. What is the problem? Nuclear force is a short range force. So as the size of nucleus will grow, there is a probability that it will go beyond the range of nuclear force. And then holding those nucleons will be a difficult task, and it will simply break. Can we say when it will break? Can we say that when a nucleus will break?
No.
So every atom, every nucleus that we, in fact, if we talk about ourselves, so if I ask Josh, how old are you? Just tell me, how old are you?
17.
Okay. But if I ask you, how old are your atoms and nucleus?
Each one will be different,
So roughly,
roughly like one. It might be from 1 minute or 1 second to millisecond. Right?
so atom is only 1 meter old.
Sir, 1 million,
Uh-huh.
millions of years, no? Billions of years.
So every atom is billion of year old. So technically, we all are how old?
Billions of years.
Billions.
We were formed at the time of Big Bang. These atoms were created in the universe at the time of Big Bang, right? And if we go by the Big Bang theory, if every atom or nucleus was created at the time of Big Bang, then how old are we in a real scale? Billion of years, maybe trillion of years, right? And if we are billion or trillion of years old, so we are really old actually. We are really old. So it is quite possible that we can disintegrate anytime. So we only know one thing, that it will disintegrate. We don't know when. But if you give me a large cluster of nuclei, then someone will disintegrate. It's like a village with people more than 90 years of age. Imagine a village in which every person is more than 90 years. It's some village in Japan. Quite possible. You can think of it. So we know that they will die soon. But can we say who will die soon?
No.
No. But we know that someone will die soon. But we don't know who will die soon. So if we talk about the probability that among this village, at least 10% will die every day or every week. Okay. And this probability will become true if the count goes to a large value. Let's say if a village with trillions of old person and everyone having age more than 90. Can we say every hour someone will go? Can we say? Every hour someone will go for sure. Now we don't know who. So again, we talk about the probability. That's what is the chance of decay of 10 nucleus out of 10 million or 10 trillion or billion nucleus. So what is the probability? So depends on how long the interval you take, 1 day, 1 week, 1 hour, 1 month. If I take 1 month, then the chance is very high, isn't it?
Yes.
Yes.
Sir.
But if I take 1 year, then it's very high. So that is the whole idea of radioactivity. But anyway, what we are talking here is not radioactivity. I'm talking about the alpha decay. And it happens due to the bulky size of nucleus. So the reason is due to bulky size of nucleus. So if we take any particle, let's say we have any particle. So let's say this nucleus is at rest. Nucleus at rest. Okay. And the mass of this nucleus is called capital M. And it will emit the alpha. So once you emit the alpha, what will happen? The X will become Y plus alpha. Isn't it?
Yes, sir.
But the moment M will become Y and alpha means what?
Helium.
Alpha means helium nucleus, right? He++. Anyway, so the question is, in the process of alpha decay, can we have some Q value?
Yes.
And if yes, then what is the Q value? If it is spontaneous reaction, it means the mass of X is more than the rest mass of X is going to be more than the sum of the rest mass of Y and alpha.
Yes. Q value will be the
So-
kinetic energy of the alpha particle.
No, alpha and Y.
Y will mostly remain at rest, no, since it's a
No.
heavy nucleus.
If it is a rest, then it will violate the conjunction momentum. Because if alpha will go this way, the Y has to go this way. Yes or no?
Yes.
Otherwise, momentum is zero, na here. So in every decay, not only energy, but momentum should also be conserved.
Yes.
Understood.
Understood.
So the Q value here, the Q value will give you the energy to not just alpha, but to Y also. But the thing is, what you are saying is in the context that the energy, the major part of energy will go to alpha. That's for sure. The majority, but it doesn't mean that Y will get nothing. Because if Y will get nothing, it will violate the what? Momentum conservation. Because a particle at rest will have momentum how much? 0. But Q value will give kinetic energy to these two particles. It means they are into motion, but how they will move? They must move in the opposite direction, yes or no?
Yes.
Do you realize this? Yes or no? Tell me. So, okay, I was talking about the Q value. What is Q value? Mass of X minus mass of Y minus mass of alpha into C square. Is this clear? Yes or no?
Yeah.
Now, this Q value will appear as what? This Q value will appear as
Kinetic energy.
Okay. Sometimes they give the binding energy and you need to calculate the Q value from the binding energy. How to do this? So let's say mass of X is known to you, mass of Y is known to you. Sorry, binding energy of X is given, Y is given, and helium is given. Can you find the Q value from binding energy? Tell me yes or no.
So we just know the binding energies of X, Y, and alpha.
Yeah, yeah. So how to do this? Okay, anyway, first of all, how to write the mass of everything. So let me show you in detail, one by one. So binding energy of X will be how much? So, okay, I need to give something more. Na? X means, okay, this is not a complete picture. Let me give you the complete picture. Just a moment. So X decays into Y plus alpha, right? So A, Z. Now what is Y here?
A
What is alpha?
minus 4.
Alpha is like, okay, I'll just start, remove alpha first. Z minus 2. So in alpha decay, what will happen? In alpha decay, the mass number will change by 4 units and the atomic number will change by 2 units, isn't it?
Yes.
That is simple. I mean, we know from class 10th also. Alpha. So mass number will change by A minus 4. I think if it is not clear, I have to clearly. Once again. So in every nuclear reaction, we can conserve the mass and charge. So below is the charge conservation. So Z minus 2. So we must have plus 2. A minus 4. So we must have 4. So in alpha decay, this is a reaction. Okay. A minus 4, Z minus 2. I hope this is clear. Okay. Not of that.
Yes, sir.
Okay, let's try to write the binding energy of each. So what is the binding energy of A, X, Z? How to write it? We know the method.
Mass of hydrogen atom. Minus mass of X.
Correct? Into whole C square.
Yes.
That is the binding energy, right?
Yes.
Okay. And binding energy of Y. Correct? So just let me know if I'm going wrong or right. I hope this is clear.
Yes.
If I subtract if I make it 1, 2, 3. What is 1 minus 2 plus 3? What is 1 minus 2 plus 3?
Mass of Y plus mass of helium minus mass of X.
Correct. This, no? So this plus mass of helium, right?
Helium 2.
Minus am I correct?
Yes.
Okay, so I should have done 2 plus 3 minus 1. That's better way of writing. So 2 plus 3 minus 1 is better way of writing. Why? Because we want the other way around. So what I'll do is, because generally they will give you this one. That's what I'm saying. You need to know this in advance. Otherwise, doing all calculation is difficult. So 2 plus 3 minus 1. How much it turns out to be? 2 plus 3 minus 1. The desired answer, right?
Yes. So, but when we calculate the binding energy of helium 2 plus, the first term of mass of hydrogen, that will include the mass of electrons, but helium 2 plus won't have any electrons. So the electronic term
No,
won't
no,
cancel.
this is the atomic mass of helium atom, not nucleus.
Okay, but the reaction
See,
will give out.
yeah. In the reaction, we have He plus. That's fine. Okay.
Okay.
Yeah. So when we are doing the calculation, we are taking the atomic mass. Okay.
Okay.
So now you can see this was the binding energy of 2 Be2 plus Be3 minus Be1 is the Q value. Do you realize this?
Yes.
How many of you realize this? This was the difficult part. So you can see what is the Q value? X minus Y minus alpha. Understood?
Yes.
And the same is here. So given the binding energy, can we find the Q value directly?
Yes, sir.
Yeah. So the way of finding the Q value is the binding energy of Y plus binding energy of alpha minus binding energy of X. So now this is the relationship between. So the way of writing, remember, is very simple. The binding energy of product minus. So binding energy of product minus reactant. This is easy to remember, right? And that will save your effort drastically. So you're not supposed to do this rigorous calculation to get the idea. So binding energy of product minus reactant directly gives the what?
Q value.
The Q value. I hope this is clear. It could be negative in some cases, but in our case, because this is spontaneous reaction, so it must be positive. Okay. Because we are doing the alpha decay. Decay means some spontaneous event is happening. So binding energy and Q value relation is clear for alpha decay. Yes or no, guys? Tell me.
Yes.
And this is not just true for the alpha decay, it is true for any reaction, any nuclear reaction. So generally what happens, you will get two types of question. One in which you have to do the actual calculation of Q value, which is slightly difficult. You need to write it very carefully. Chance of making mistake is also very high. And the other case will be when they give you the binding energy. Okay. And I'll tell you something very simple. The moment you have the value, just check that the reactant energy, the total reactant energy is, and the total product energy is how much. That's simply check from there by adding and subtracting. And if you see there is a if the sum of the product is more than reactants, that is the Q value. Okay. And that Q, with that Q value, you can do the further calculation. I'll tell you what. So we got the Q value. Now we know the decay is a so alpha decay is a very common question of collision, which we have solved many times. So a gun will fire a bullet. So gun will recoil, isn't it? So when a nucleus will disintegrate, so when a nucleus will disintegrate, it will also recoil, isn't it? And from the conservation of linear momentum, what we can say? So this is A minus 4y. Okay, so how to write it? Conservation of momentum. For the time being, I'm writing capital M and small m, just to make it easy. So what we can write? Conservation of momentum. So the simple way of writing the momentum of y must be equal to momentum of alpha. Yes or no? Tell me, guys. Simple relation.
Yes, sir.
Or you can write as 0 equals to P alpha minus P y, the way you want.
Yes, sir.
I hope this is clear.
Yes, sir.
From conservation of energy, the total kinetic energy of the system we can write as Py whole square by 2my, P alpha whole square by 2m alpha equals to Q value. Tell me yes or no.
Yes, sir.
Any doubt so far?
No, sir.
And we know that both are equal. P alpha equals to P y. So we can replace this is P by 2 common. P square by 2. What we are left with?
1 by my, 1 by m alpha.
So P square by 2 is how much? My m alpha upon my plus m alpha
Into Q.
into Q. So kinetic energy of alpha is how much? It is my by my plus. So kinetic energy of y is how much? Is it 0?
M alpha y.
Mm.
Y plus.
You have it. And this is even easier to remember, because what is my? My means, because it's a ratio, no? So can we write my as simply a minus 4? Because the common term will cancel out from everywhere, right? And my plus m alpha is how much? A. Tell me, guys, yes or no? So this is the famous formula of alpha energy. Kinetic energy for alpha particle is how much? A minus 4 by A whole into Q. And if you add these two,
Q.
JEE-Mains 2021. Just formula, you just apply the formula, you will get the answer in one line. In fact, they had given the Q value. Is this clear?
Yes.
Yes, sir.
Yeah. It's very simple. In alpha decay, what they will ask you question? Whether you're writing bits Pilani examination or J advanced or JEE-Mains, remember this formula. That's it. A minus 4 by A into Q, 4 by A into Q. That's it. This is the most important derivation. And how to find the Q value? If the binding energy is given, you know it.
Yes,
Product
sir.
minus binding energy.
So it's a binding energy of Y plus alpha minus X. That's it. So it depends on what is given to you. All right. So why alpha decay happens? Clear? I hope so. So in
Yes.
most of the alpha decay, the nucleus that we obtain is not always stable. Of course, it is relatively stable, but not stable. Because alpha decay will never assure you that what fraction the nucleus, I mean the quarks will distribute. So you know how many neutrons has gone, but do you really know how many quarks has gone? How many up quark, how many down quark? So that is difficult to. So in most of the alpha decay, it is always accompanied by a beta decay. Beta decay is like, every time you disturb the equilibrium distribution or configuration, you need to rearrange. So let's say you have your study table in which everything is kept, nice way, in ordered way, and then some younger cousin comes and just throws everything away. Okay, so you may lose some of the pen also, just like alpha decay. And then what will happen next? You will rearrange, but when you rearrange, with the remaining amount of stationery, the arrangement will change. You will have a new different arrangement. So it's called the newer configuration, and therefore this new configuration will try to acquire or achieve even more stability than the stability you got during the disintegration process. So it is obvious to study the beta decay. Okay. So let's talk about the beta decay. Beta decay. So beta decay will have two types. So the most famous one is called beta minus decay. And we also have beta plus decay. So in beta minus decay, what happens? A neutron converts into proton, but I'll write it in detail. So I'll write one by one. This is also called positron emission. Positron emission. You can say this as electron So this electron is coming from nucleus, and we all know that an electron cannot reside inside nucleus. Yes or no?
Yes, sir.
So electron has to leave the nucleus. So once it is formed due to the nuclear transformation, so it is allowed to be formed there, but not allowed to be remain there, because that will be the violation of the Heisenberg uncertainty principle. So it has to leave the nuclear dimension. So when happens beta decay, let's see. So when n by p ratio, okay, is more than 1. So we got the lighter nuclei, but the ratio is still more than 1. What needs to be done? So because the n is in excess with the proton, so some of the nucleus neutron will convert into proton, isn't it?
Yes.
So neutron will have mass 1, charge 0. The relative mass is 1, and the relative charge is 0. Proton will have a relative mass 1 and charge also 1. So if you conserve the charge, the bottom one, how much we should hear?
Minus
And if you conserve the mass, then how much mass?
0.
This is called the relative mass, not the absolute mass. So which particle will have zero relative mass and -1 charge?
Electron.
But this electron is not the electron of your atom. This is the electron produced during the transition. That's why this is called beta particle. So this is your beta minus. This we call beta minus. Okay. But in every nuclear decay, not only the particles will form, because apart from the particle, what you will get is also some energy, radiation, some electromagnetic radiation. And what really comes here is called the nu bar. How we read? Nu bar. And this nu bar is called
Antineutrino.
antineutrino. So how to remember? See the beta minus and bar. Simple way of remembering. So they will also ask you this question that in beta minus or beta plus, which decay we will get antineutrino. So the antineutrino itself is the electromagnetic wave. Understood? So what will happen to, okay, this is the one way of writing, but the actual way of writing will be how much? How to write the beta decay for nucleus? So let's say we have a nucleus X. If it will undergo beta decay, what will happen?
A will remain the same and Z will become Z plus.
So A remains same, but Z becomes Z plus 1, isn't it?
Yes.
So what about the Q value? Let's calculate.
So here, what does the antineutrino conserve?
It is pure energy. So energy of a antineutrino we can address HF, let's say frequencies F or nu whatever.
Yeah.
This is the notation, but you can assume let's say frequencies. Pure energy. So it is a pure energy electromagnetic wave, EM wave. So it is a pure energy. It's a EM wave of, let's say, frequency nu. So how to add the Q value? Tell me.
Mass
By
of neutron
definition?
minus mass of proton minus mass of electron into P.
So Q value means we have to add the nucleus, no? So mass of AXZ minus ZME
Yeah.
minus MAYZ plus 1 plus Z plus 1 M plus ME. Tell me if you get it, yes or no. Do you get this? What I have written here?
Yes.
Just look at this. If you are okay, then I'll go ahead. Else I'll do something. Oh, I have to subtract here. One mistake. Minus. Yeah. And if you look carefully, then all Z, all ME will get cancelled out everywhere. Yes or no?
Yes, sir.
Yes, sir.
So it is eventually left with AXZ minus AY Z plus 1 into C square. Okay, tell me common sense, by common sense. If X forms Y, so Y is more stable than X. correct?
Yes.
And if Y is more stable, then it will release more energy, means more binding energy, yes or no?
Yes.
So binding energy of Y will be more than X.
Yeah.
So this is the answer of Q value. Because we don't have other particles, right? Electron is taken care here. So this Q value we can directly write as binding energy of Y minus binding energy of X. Do you realize this, yes or no?
Yes, sir.
Tell me guys if this is clear to you.
Yes, sir.
So because I have given you the formula that Q is always binding energy of product minus reactant, right?
Yes.
And so here we have the product as Y and X. Okay. So I hope this is clear.
Yes.
Hmm. Okay. There is a very common question that is asked.
Include the energy of the antineutrinos, no? HV.
Just my bad, my bad. A big mistake I have made.
But Q is just the kinetic energy. So
No,
there
no. Now the kinetic energy will be not Q value, because out of this energy, some energy will be taken by the
antineutrino.
So the kinetic energy of this will be Q minus energy carried by this.
Yes.
So this I have to mention this explicitly. So I will write somewhere. Now, whenever we have a radiation, then we need to consider the kinetic energy as Q value. And out of some, see, always remember that radiation is energy which has come because of the nuclear reaction, the change of mass only, isn't it? So it is the mass which forms the radiation. So it is the conversion of mass into pure energy. So the kinetic energy remaining will be Q value minus what?
HV.
Energy of radiation. Understood?
Sir, but Q was defined as the kinetic energy of the product, right?
Yeah. It is defined. So there is a way of writing. I'll tell you how. This is also way of writing, but we can convert every mass into equivalent energy into equivalent mass. Okay, so I could have it then somewhere here. Okay, I'm just writing for your understanding. Plus h nu by c square.
Okay. Yeah.
So what that will do is this h nu by c square into c square will make it h nu.
Yes.
So actually you will get Q as minus h nu. But if I write h nu here, the problem is I cannot equate with BEY BEX. That's the problem. Are you getting a point? This represents Q value. So in case of absence of radiation, if it is pure nuclear transformation, there is no radiation emitted, then the Q value will be kinetic energy. The moment you have radiation, there are two ways to accommodate. Either you keep it explicit, which I have done here, or if you want to include, you can include with converting this energy into mass equivalent. The same Einstein formula. E equals to mc square. So M equals to how much? E by c square.
Yeah.
So choice is yours. How you want to go. What I have done this way, there is a pure reason for this. The reason was I cannot write this answer. So okay, I can write it to method 1. And then we can say kinetic energy equals to this Q value minus H. So I can say this is Q effective. Let's say this is Q effective, a new Q value. Okay, so this is not Q effective, this is Q. And this is Q effective. Can we say like this? The effective Q value.
Yes.
So we are making a modification. or the other way around is the same. So if you want to stick to the definition that it is the kinetic energy, then what you can do? Mass of minus and if you do so, you'll get, I think, so now this is the Q effect. We are getting the Q effect is directly, right? So this we can attach. So again, you have choice to write. And I'm not wrong. The way I have explained, we can manipulate things as per the situation. Is this clear?
Yes.
So if you really want to stick to the definition, then you have to make this some arrangement. You know what I mean? Okay.
Sir.
So this is very crucial. How to write the Q value. See, the most difficult, see, in JEE Advanced, this question will come. If you have not practiced the basic, like the way I'm deriving it, you have to practice the derivation to understand what is happening. And although I would say it's very easy, but if you will not practice enough during the examination, you will find it's some Greek and Latin only. So we'll solve some question of JEE Advanced to see. So beta minus decay is okay. So
Yes,
in
sir.
beta minus decay, what is happening? The mass number is same, but the atomic number is changing. So, so we are moving one step ahead in the periodic table. So how to get isotopes? How to go back to the same position? So in one alpha decay will, if it is alpha decay, yes, Z will decrease. So if X is here, so after alpha decay, I'll add something like this. I'll make a diagram. In periodic table, if X is here, if it will make alpha decay, it will go back by 2 value, right? Isn't it? Tell me, guys. Are you getting it? But in beta decay, you move one step forward. So of course, this is not y, it is x, it is y now. It is y dash. My bad. Let me make it better. And if it will undergo one more beta decay, so you will go back to the same position, right?
Yes.
So 1 alpha and 2 beta decay will create the isotope.
Yeah. 4 less neutron.
Pardon?
Neutron number will decrease by 4.
Correct.
4.
So this is called the, what this is called? Soddy displacement law, something, na? There are two guys name, Soddy and, tell me guys. Soddy-Fajans displacement law. To create the isotope. Okay. Okay, as in beta minus decay we are done. So next is beta plus decay. Now that's something dangerous. So beta plus decay, what will happen? The N by P ratio is less than 1, which means proton is really too large in number. Proton is too large in number. Okay. So to become stable, we need more neutron and less proton. What we need? So when a nucleus will have this situation, it will have two possibilities. So what is the possibility? You want to convert P into N, isn't it? But it is like you have to flip one of the up quark into down quark. Yeah, you have to. But converting the up quark into down quark requires extra energy, but down quarks are heavier. So this conversion is accompanied, you can say, is achieved by two processes in nuclear world. One is the beta plus decay, and this is called the rare process. Rare. Other is called the K electron capture. And these two processes compete with each other, and the winner is definitely K electron capture in most of the cases. So this is high probability. But this process will be low probability process. So we'll talk about both the processes one by one. So beta plus, because I'm going to discuss. Yeah, that's the.
So I had a doubt in beta minus decay. Then the spin should also be conserved, right, in the particles, because there's interconversion happening. The spin angular momentum should also be conserved, right?
No, there is nothing. Spin should not be conserved. Spin will be there, but if you change the quarks distribution, the spin will change. So because of that only, the energy will change overall. Okay. So
yeah, but
momentum,
momentum, like the spin corresponds to some spin angular momentum. So like neutron, proton, all of those will have some spins, right?
So spin will give you the energy configuration also. So you can think like a angular momentum and energy relation in L square by 2I, something like that. Think about it. So a different energy configuration means a different spin configuration also. So we cannot say spin will be conserved. We can only say that a spin is there, but we cannot conserve the total spin, because here the spin is related to the system, but system is getting distributed, no? No, understood.
But doesn't the spin also correspond to its own type of momentum? So that type of momentum should be conserved.
No, why it will conserve? Because see, what you are doing is, if you convert, let's say, one up quark into one down quark, is it conservation of the spin?
No.
So you're changing it, rather you're changing the spin. And to change the spin, you need some energy.
Okay.
You can think that this way. Take a,
Okay.
a gyroscope and spin it and try to turn it. You need to put effort actually.
Hmm.
It's very difficult to turn while it is spinning very fast.
Yes.
So that means it requires some work done, right?
Yeah, but it's still a spontaneous process, no? So the
So it is
external
getting it is getting energy, no? Through the nuclear reaction. The mass defect is giving you the required energy to do this process.
Okay.
Understood? It is like you're going to a new quantum state, which is more stable. Quantum, see, the idea is the overall quantum state should be in a more stable condition, not individual. So spin can change. Why not spin will change?
Okay.
I mean, it is like more logical. Spin should change because we are changing the energy configuration.
Okay.
And that is the reason behind the adiabatic cooling process. Imagine if you suddenly you have a liquid water. Imagine you have liquid water, H2O. By some mechanism, I change the spin of every proton in the entire water. And that will require tremendous energy to reverse the spin. Understood? And that will lead to the sub-zero temperature of the water. In fact, this process is achieved in cryogenic. We do this process. We apply the very strong field, we reverse the spin, and we make it cooler.
Oh.
So this is called adiabatic cooling process.
Okay.
Or you can say adiabatic magnetization and demagnetization process. So we do have something like this in physics. Very interesting topic to be studied about in superconductivity chapter. Okay, anyway. So isotopes are made. What you need to know is this reaction. This reaction is spontaneous. Why? Because we are moving from the high mass to low mass configuration, which means the energy will be available in the process. So it means we are going to achieve the better stability with less energy value. But this is something interesting. The beta plus decay. What is happening here? A proton converting into neutron. Oh my God. What we need here to conserve? Do you realize this?
Yes, sir.
111001. Mass is conserved, charge is conserved. And this is called neutrino. Understood? This is the neutrino. Now, this is iron. What is happening here? In the due process, the mass is increasing or decreasing? Can you guess? Mass increasing. So it means we are converting energy into mass. That's God's particle, you know, the LHC which happened in 2012. Einstein said mass can be converted into energy. Higgs said, can we do the reverse? Can we convert energy into mass? Because that could complete the entire assumption of Einstein theory of, you can say, energy mass relation, the famous energy mass relation. And it was achieved. So they developed some, I mean, for some trillionth of a second, the particles that they observed in the LHC had mass roughly 200 times more than the mass of proton. So that set, we see you're colliding proton, you're getting something heavier. So it is like I'm giving you only copper, you're giving you gold. So you must be alchemy. Okay. So in the LHC, what happened? They collided the high energy protons and they got something heavier, which was a proof that, yeah, mass energy can also be converted into mass. Now, this reaction, can it be spontaneous? Can it be spontaneous? Tell me.
No.
This is non-spontaneous, which means This cannot occur in isolation. This cannot occur in isolation. Generally, what happens, this reaction is although rare, but it has occurred. But in a cluster of nucleus, it means a large number of nucleus is undergoing nuclear reaction. And what you're doing is you're taking someone else's energy and carrying this reaction. Are you getting my point? The energy requirement of the NAC, every chemical reaction will have some thermodynamic requirement, some energy requirement. So that energy requirement is getting fulfilled in the due process by someone else. So if you try to create this reaction in isolation, it will never happen. It only happens in cluster. You know cluster? When we have large number of nucleus undergoing some transition and the energy released by some other transition, you take that energy and you carry your reaction. So that's what I said, this is a rare reaction. Now, suppose if the number of proton becomes really large in number, if the nucleus will have too many protons, the orbiting electron in the K shell will be under danger, under threat, isn't it?
Yeah.
Because anyway, the electron is, in the probability space. So it is away from the nucleus, but it is in the probability space. So the distance of the orbiting electron in the K shell will vary from the nucleus because of some uncertainty. And it is quite possible that you may go close enough and the proton is so powerful, it will just swallow it. Because it's too much charge, eh? The nucleus is full of charge. So the K shell electrons are under danger, under threat. So in the K electron capture, what happens? A proton eats up electron and what it creates? Understood?
That's neutrino.
Oh, sorry, yeah, it is again neutrino, same thing. So technically, if you look at the reaction, it's very close. It looks like both are same, but they are not same. Because now the reactant has increased in the second case, isn't it? So how to write the reaction in terms of atomic masses? So I'll just show you. X beta plus decay A Z. If it is beta plus decay, what will happen? Z becomes, tell me guys, Z plus 1 or Z minus 1?
Minus 1
A
remains the same.
Remains unchanged.
Unchanged.
and then we have what we have 1 and 0, right?
E positive.
Okay. So what is the Q value? Tell me. Am I right? So how much we're getting the answer? Tell me, guys.
Bond energy of, in terms of bond energy or? in terms
No,
of
right
boson?
now, without bonding. If you look at this equation. You can expand it. So you get something interesting here. See, you have increased the twice the mass of electron. Now the electron will not cancel out. Understood? So Vy minus Vx. Hopefully. And I can guess that this term is going to be negative. By the way, it is also important to remember the energy of electron in mega electron volt. Okay. So what is the mass of electron? How much?
9.1 into 10 raised to minus.
31. So if you want to convert into the mega electron volt, what is the equivalent U, AMU of the electron mass? So this is how much? So we know mass of electron is I think roughly like this.
Yes, sir.
So I think this should be roughly like this. And this is roughly 0.5. Isn't it? Roughly, not exactly.
Yes, sir.
So you just need to remember this value also. So I do this calculation 931.5 divided by 1837. So 0.507, but we remember as 0.51. So this is a famous answer. So you need not to worry about this. MEC square is roughly. And this answer you are supposed to remember. So no need to do the exact calculation. You can do like this, the way I did it. So will you remember this answer?
Yes, sir.
Yes.
So a lot of information you need to remember. That's why here, if you know the binding energy of this thing, this will become how much? 0.5, 0.5 means 1.
1.
Okay, 1 MEV, and yeah. How much? 1.02. No?
Huh.
And this I don't know. So this is the answer, and this will be mostly negative. So such reaction will not be spontaneous, right? For such reaction which is not spontaneous, you need to impart the energy to make this possible. I hope this is clear. So what we do in such reaction? If let's say if I want to carry out some reaction in which the reaction is endoergic. So how to carry out endoergic reaction? Any guess?
So energy though we'll need to supply, but like condition like for beta plus we needed N by P ratio less than 1.
Yeah, beta is different. I'm saying a general endoergic reaction. So there we use there is an idea of projectile. So you bombard it actually, because you know that the energy which you provide in excess, that energy will overcome this that you can say difference. Okay. So that is very, very crucial. We come to this. Now this is non-spontaneous. I have written this somewhere, I think. Yeah. But this is so experimentally you can say whenever N by P is very small, it is found that the K electron capture is preferred over beta plus decay. So what they will ask you, that which two processes compete against each other? The answer is beta plus and K electron capture. Okay, so these two processes compete against each other. So this could be a potential question of JEE-Mains as a theoretical question. Okay, next. So remember, I'll solve some questions, some G advanced questions, so that you can correlate things. Okay. Next. So there is a very nice question. Now I just remembered. In alpha decay, the alpha particle which was released, okay, I'll just go back to this question, is sent into transverse magnetic field. If alpha decay, if alpha particle is sent to uniform and transverse magnetic field, so it will perform the circular motion, right? Yeah, I hope you remember. And let's say R is the radius. What is given to you? R is given to you. And the alpha particle is moving like this. No, it's left side. Okay. So what is the formula for radius? mv by qb, which you can add as momentum of alpha upon 2 ev. Tell me guys, yes or no?
Yes.
So what is p alpha? Sorry, qbr. So what is the kinetic energy of alpha? And we know that kinetic energy of alpha is, so what is the Q value of reaction? So we can ask question of magnetism like this. Understood?
Yes, sir.
So you can convert one question into question of magnetism, then we can use the the same question. Let's say if I create a interference using alpha particle, you can do anything. Just keep your eyes and mind both open. You can relate stuff accordingly. Anyway, this was just a question. I just got to came to my mind. I thought of explaining. Next. Okay, so Q value for K electron capture. So in K electron capture, what is happening? Tell me, guys. Correct. So so how to write Q value? And you can see again, this will cancel out now, right? You can realize for yourself. Ah, okay. We got the answer. This is back to the same answer. So you can play with the idea.
Sir,
Yeah.
in K electron capture, just like X-rays, we'll be able to observe K alpha, K beta, all those radiation.
Pardon? In like K electron capture,
In
the nucleus
X-rays, we had
will
also done that.
will
K shell
yeah,
electron.
yeah, K shell electron. That's right. Yeah. Correct.
So here also we'll be able to observe the K alpha, K beta radiation. Right?
Ah, yeah. Quite possible. So if it is happening at an atomic level, then you can observe. But if it is happening at nuclear level, then it won't happen, right? Because in nucleus we don't have. Okay, but the whole idea is it's happening at a atomic level only.
Yeah.
So this will happen. What you're saying. So we may get some X-ray also emission, but that will not contribute in the calculation of Q, right? Because that is because of the transition of
that's later.
electron. So, so that energy is coming from a different configuration. So we are not bothered about the Q value calculation. Okay.
Okay.
All right. So how many of you think that you can write this equation from scratch, even if you don't remember the formula? Okay. But you need to practice. If you are not finding yourself in a comfortable position, then keep on practicing till you find it. There is no way out. I mean, see, nuclear physics is very easy. Just few formula and we get the answer for sure. But the thing is, you really need some patience and some good practice over this very tiny calculations. You have to be very careful. I'll just solve some advanced question, subjective question of old yesterday years. Okay, gamma decay I have already discussed. What is gamma decay? When any excited state of nucleus goes to the ground state. So it is the change of configuration of some meta state of a nuclei to the stable state. It releases some energy, that's called the gamma radiation. And in gamma radiation, what happens? You just reconfigure basically your quarks configuration. So that is all about gamma radiation. So we'll not go in detail of gamma. There is nothing to be worried about gamma, but there is one thing that we should know about gamma. Absorption of radiation by media. So if we have a medium, and let's say if some so this is a gamma rays of intensity I naught comes here, and X is the thickness of the medium of absorptivity mu. Okay. So what will be the intensity on the other side? So let's say, okay, we have to solve the differential question. Let's say the intensity at a distance x. I mean, of course, here this is also I'm taking variable as also as x. So x is I, and at a distance x plus dx, let's call the intensity as I plus di. So while crossing this medium, if you walk by the elementary value, the intensity will also change by the elementary value, and it is going to decrease or increase.
Decrease.
So what is the change in intensity? So change in intensity is how much? Di minus di, basically minus di, right? So what is the fractional? What is the fractional change in intensity? Fractional change in intensity. Can we write this as minus di by I?
Minus di by I.
And it is found that this is proportional to the distance traveled, dx. So minus di by I, the fraction change is proportional to dx. So we can add this is equals to some constant. This constant is called absorption coefficient. Don't take as a refractive index. And therefore, we can integrate. So the answer will be how much? So it is exponential relation, right? I hope this is clear.
Yes, sir.
So you can apply for the gamma or X-ray or whatever. So this formula is true for any medium with known absorption coefficient. So this is how the intensity will vary as you go across it. So this question, let's say this is not part of JEE syllabus, but they may give you as a comprehension and tell you to derive it. So it's good to know. Yeah, there is nothing like a JEE syllabus. JEE is undefined boundary. Whatever they want to ask, they will bring into syllabus. So you don't have the control over syllabus, but you do have certain control over the concept at least. Next. So I think all decays are done. Okay. Alpha, beta, gamma. So now we can go back to the radioactivity. Radioactivity. So as you said, radioactivity is what? It is the spontaneous. Tell me. Tell me, guys.
Disintegration of the nucleus into relatively stable.
Yeah, correct. So you know the simple definition of radioactivity. So what exactly is the law of radioactivity? What is the law? In physics, we don't talk about the. Okay. I just mentioned this. Okay, one more question. Okay, before I start the radioactivity, I talked about the endoergic reaction. Which means Q is going to be negative. So let's say if A will act as a projectile which you throw with some speed, and it is going to hit the A, and as a result, some new nucleus B and some new particle B will form. We are not considering any radiation. In every reaction or because it is simply chemical reactions are basically collision. Okay, if it is happening in things like this scenario. So every chemical reaction is some sort of collision, because if you have studied the chemical kinetics, you must have come across the collision theory of molecule, right? So we do have something called collision theory and the order of reaction. Have you heard this?
Yes, sir.
Collision theory? Oh, okay. So now the question is, what if Q is negative? So how much kinetic energy this must carry to carry out this reaction? Because in the reaction, we need to increase the value by Q value, the mod of Q, because the answer is negative. So how much energy we need to give? This the mod of Q is the. What is mod of Q? Okay, what is Q by the way? The Q value is here is how much? MA plus M capital A. And what I'm saying is this is negative. So how to carry out this reaction? Tell me.
So we'll have to supply this much energy by the kinetic energy of the A which we are projecting.
So should I give the kinetic energy of the projectile more than or equal to the mod of this?
Yeah.
So if I give equal to this value, will it happen? Will this reaction occur? This is the rest mass energy. It means you're considering that after reaction, everything is at rest. If after reaction, everything is at rest, what will happen?
Momentum will conserve the violated.
Yeah, so there is a violation of momentum conservation.
Yeah.
Because A is coming with some velocity, so A is having some momentum. So B and B must have the same momentum together.
Yes, sir.
So I'm saying if Q is negative, then how to carry out the reaction? Let's call this for simplicity. Let's call this is M. This is capital M. So we know that the energy available in the CM frame can do the magic. If the kinetic energy of system in the CM frame is equals to mod of U, your job is done. Or you can say more than equals to this. So for endoergic reaction, because the energy of the center mass will will conserve the momentum, yes or no? Energy of the center mass will conserve the momentum.
Yes.
Yes.
So you need that energy also, no? The energy of the center mass, because that will conserve momentum, and then you need extra energy to carry out the energy change of the reaction, the Q value. So basically, the kinetic energy of projectile should be equals to what? Kinetic energy of center of mass.
Plus Q.
Understood. So the energy in the CM frame, not CM, this is the energy of center of mass. If this is met, if this condition met, then reaction will be carried out. So only Q is not sufficient, because if you say this is equal to this, then the violation of momentum will take place, isn't it? Are you getting it? Tell me honestly.
Yes, sir.
Yes.
Yes.
Okay. So those who don't know, there is a direct formula you can apply. So kinetic energy of system with respect to CM frame having a formula half reduced mass into U relative whole square, isn't it?
Yes.
If you remember. And the reduced mass is and the U relative is V only, because this is at rest. This is V. And if you look carefully, half mv square is what? This is called kinetic energy of projectile. So to carry out endo-ergic reaction, the kinetic energy of projectile into m by m plus m is mod of Q. So the kinetic energy of projectile is how much? You can clearly see it is more than capital Q modulus, right? Understood?
Yes, sir.
Hello.
Sir.
So this is called threshold energy for endo-ergic reaction. What is the threshold energy of projectile? This is the threshold energy of projectile. So this was the, I think this was the JEE advanced question, if I not incorrect. Okay. All right. Let's do some practice problem. At least 1 or 2 questions, so that you can do some calculation. Do you have the JEE advance 2022? Yeah, 2022 paper. Anyone have it?
Yes, sir.
Yes, sir.
Open it, just see if you have this question. I think this question should be there. Meanwhile, I'm giving you one question. Consider the beta minus decay of gold to mercury I don't know how this value is. 197. This should be 197, right? 198 only. Yeah. Where Hg star represents Mercury, I don't know. Nucleus in an excited state at energy 1.088 megavolt above the ground state. Oh, nice. What can be the maximum kinetic energy of electron emitted? Yeah. What is given to you? Okay. As I said, they'll give you the actual mass 197.968233 and you 197.96676. Okay, fine. Can I do the calculation, guys? So what is the Q value? Do it fast. You can take, see, in JEE, they will also give you that one U is. Now, if IT is saying take this, then take that value. I'm giving you this is the by default value. So for some to make the calculation easier, they tweak the value. So they will tell you, okay, take 932 or 9035. Maybe that is giving you the integer value, something like that. Solve this. I think 3 minutes more than.
Sir, for mercury, what is the mass after 0.96? 197.96.
Okay, it's a 968.
Okay.
Sorry, 96 just now. 966. 966. My bad. 966. Just get the Q value there. After that, it's a one line question. Okay, time up. So you can just take the difference of these two, right? So what
Sir,
is Q value?
0.49 something. Mega electron.
I won't say something. Tell me exactly.
So like
You have- you
till
have
how many
decimal.
digits we have to round off? 3, 4.
After decimal, at least 4 or 5 digits.
Oh, okay.
Okay, so let me find the Q value. What is Q value? 197.968233. 197.96676 into 931.5. Correct? This is the answer. Tell me guys. The
Yes,
first
sir.
one. 197.9682. In advance also you have to be very careful with the calculation. They generally take the range, so no need to worry much. But you have to be very accurate. 1.37 20995, right? Okay, you can't take the approximation because this is anyway very small. See,
Yes.
this is the energy with the assumption that the mercury atom obtained, the nucleus obtained, is in the ground state, right? But actually, what we are getting? Some excitation in the mercury atom, isn't it? And you can see the energy of excitation is how much? So out of this energy, this much energy is already used by the nucleus in the excitation process. Understood?
So we'll subtract.
So that's it. P max is Q minus. Whatever the answer is, the answer. Minus.
0.28409.
So this is 0.284.
409.
Correct. That's it. Simple question. Any doubt in this? So I would like to give you some question from the JEE. Where I can give the question. Okay, I'll share this question. Okay, I have sent some question. Can you see? Solve question number 74. 75. Oh, that's very easy. Seventy-four, 75. And what else? Mm. $81. Okay, anyway, you can keep on solving. I'll share a question. You can solve a lot of questions. I'll share with you. So I would like to proceed as much as possible to the. Can we start the radioactivity?
Yes, sir.
Okay, in nuclear fusion will have reaction which you can calculate the Q value in the same process. Okay, now we'll go to radioactivity. Law of radioactivity. So what is radioactivity? It's a statistical process. It's a so in chemistry, you study as a first order reaction, but in physics, we study as a theory of probability. And as I said, every nucleus is very old. Okay, and because they are very old, so they can die anytime. So every statistical physics or every statistical process will have a model or some mathematical playground, you can call it. And this mathematical playground is only applicable or valid when the number of, you can say, specimen or particles or nucleus is huge, extremely large. So for if you, let's say if you have 10 nucleus, we cannot talk about the law of radioactivity. So statistical models are a very approximate model, and it mimics the real world for large number of particles. If we have a small number, then it will never mimic the real world. So it will not be a valid law. So what it says is something very simple. Let's say if you have a if you have infinite, so it's a poultry farm with eggs, infinite eggs. Let's say we have infinite. So we talk about something called uniformity. So we have some we have a phenomena which is going to happen in a uniform way. So what is uniform? So let's say if you have at t equals to 0, if you have n number of nucleus, which nucleus? Unstable nucleus into this, you can say basket or whatever. Imagine it's like a poultry farm. And at any time, any egg can break and some chick will come out of it. Now the thing is, after a moment, E plus dt, the n will be less or more.
Less.
So let's call it n plus dn, where dn is going to be negative, right?
Yes, sir.
But mathematically, what do we assume? N plus dn, right?
Plus.
So how many nucleus has disintegrated in the time dt?
dn.
Number of nucleus disintegrated in the time dt.
DN.
dn.
No,
Minus dn.
minus d. Correct. Because the next value is going to be small, no? So dn is going to be negative for sure. So we
Yes,
put
sir.
minus to make it positive.
Positive.
So number of nuclei disintegrating in time dt is minus dn. Okay. So what is the probability? So what is the probability of breaking of dn nucleus out of n? Come on. What is the probability of disintegration of DN nuclei out of N nuclei?
dn by n
No,
minus dn by n.
this is called the probability. This is the probability. Okay, this is the probability. In how much time? Time dt. Time dt. So we can call this as dp. So here dp is the probability, right? So
Per dt.
what is the probability per unit time?
1 by n dn by dt minus 1 by n.
So it is up to you to write. Now, can we assume theoretically or by common sense or by statistical means that as long as n is very large, every dn will have roughly same probability?
Yes.
So this
Yes, sir.
probability will be constant value over a large time as long as n is really big in number. So that is the statistical model that the probability per unit time is a constant entity in the law of radioactivity. So dp by dt will never change. It remains constant. So this term is a constant. And this constant we represent by. So what is lambda? What is lambda actually? Probability per
Yes.
unit
Time.
time. That's it. So that is the physical meaning of lambda. Now, this is not what we study in chemistry, right? Chemistry, we have a very different interpretation. But the law of radioactivity is not chemistry. It's a pure mathematics. So this is called statistical physics. Or you can say you can simply call it statistics. Because only guess can be made. Can we really understand the such phenomena in nature? So without the statistical model, it's almost impossible to deal with such, right? And you can see the lambda, the probability, we are assuming that the probability per unit time is going to be a constant value. Because for every time dt, the dn by n will be roughly same. Okay. As long as n is very large. Now let's say you start with 4 billion nucleus, and every second, let's say we have 4,000 disintegrating. After sufficient time, the number left will be, let's say, 40 lakhs. Now 40 lakhs and 4,000 is not, the ratio is not very small or insignificant. The ratio becomes significant, right? So now it will deviate from the statistical model. So now it will not follow the model. The model will break. So for model to continue working, the n should be as large as possible. And that's the case also, that we need to worry that in real life also. The beauty of the radioactive decay is that as the number goes into the lesser amount, as the number will decay, the rate of decay will become very small, such that they maintain the probability. It means they will never become very small. Are you getting my point? The rate will become very slow.
Sir, but why will the rate of decay depend on the number of molecules? Because that's like an intrinsic thing of each molecule.
No, it's very
not
common.
different.
Let's say common. It's like a see, if I give you only 4 eggs, okay, just 4 eggs, and imagine when the chick will come out of it. You may wait forever and it will never come out. Quite possible.
Yeah.
As the number will grow in value, the probability will grow for sure.
Yeah.
The chance will grow. Let's say if you have 4,000 eggs, then someone will break. I don't know who, but someone will break.
Yes.
So if I make it to 1 billion, then at every instant, someone is breaking somewhere in the world. Now, if the number becomes too large, let's say, because see, even if you talk about the 1 mole is how much? 10 power 23. That's a tremendous number. So
Yeah.
if you try to comprehend that number, it's difficult to even comprehend. So how big is 1 mole? If you go to Arctic, North Pole or South Pole, if you look at the night sky, you can see cluster of stars. Even that is less than 1 mole. Do you know this? So, I mean, whatever human eye is able to visualize the entire universe at one go, that will not exceed the 1 mole. So 1 mole is something really huge. Okay. So as the disintegration will occur, the 1 mole will become half mole. Half will become 1/5, or will be 1/4, 1/8. Now, see, the T half itself is in thousands of years. Imagine. So after, I mean, to undergo 4 T half, a million will pass. Not millennium, like decay, thousands of years will pass. So carbon is having roughly 5,000 to 6,000 years of half-life, right?
Yes.
And the iodine will have some hours, maybe 30 minutes, 20 minutes. So that's why the tincture iodine is used for the some diagnosis. Okay, so if we want to know that where is the blockage in the blood, so what we do generally is we add the radioactive iodine into the bloodstream. Within few minutes, it will spread out the entire body. And through some Geiger-Müller counter, we can check where is the large radiation, because the clot will make the concentration of the iodine more near the clot, and therefore you can count more. And that will give you the idea, okay, there is a blockage in the vein, in arteries, and so on. So this process is used mostly in I think in medical science, they use this technique. So the radioactivity having, of course, practical uses also, but the half-life can be very small also, the half-life can be very large also. But the idea is the law of radioactivity is only valid for, it's a mathematical law, no? So I'm saying the reality is happening the way it is happening, but the mathematical, you can say, model will not hold true if n becomes countable, like very small. Countable means it's very small. Let's say 10 power 5, 10 power 3. In that case, it will not work. 10 power 23 is okay. 10 power 22 is also okay. 10 power 20 is also okay. Okay. But if you go below that 10 power 10 or 10 power, because the disintegration units are in 10 power 10. You realize this? In 1 second, 10 power 10 nucleus disintegrate per second. So how many seconds we need to disintegrate 1 mole? Imagine. How much?
Raised to 13.
Seconds. You know how much is this? In years?
Many years.
So 86400, 365 years. Isn't it?
Yes, sir.
Yes.
Let me do this calculation for you, just to give you some insight. So 10 power where's power? 13 divided by 86400
Sir, somewhere
divided by
around
365. Oh my
3
God.
lakh 17 years.
Can you imagine?
3 lakh 17,000 years.
At a rate of 10 power 10 disintegration per second, because that is the unit of Curie. So 1 Curie is basically 3.7 10 power 10 DPS, disintegration per second. So at a rate of that large value, 10 power 10 is a huge value, but still it will take lakhs of years. A human life on the earth is less than that, right? How big, I mean, how long is the human life on earth? Okay, anyway, I was talking about something different, not this. Okay. Here, what I'm saying is try to understand the way I'm trying to explain, not by the way you understood in the chemistry. What I'm saying is, as long as n is very large, the dm by n remains same, roughly. because the change will be in the 10th place of decimal maybe, or 20th place of decimal, but that is okay, na? So probability is a fraction. So n is 10 power 23 and dn is, let's say, 10 power 10. How much is the value? How small this value? Very small. So if you make the dn, if I make it a 3, 4, 5, the change will be roughly almost same, na? So kind of constant we can also feel, right? A small change of dn, if you make dn by changing by small value, then dn when will remain almost same in terms of numerical value.
Yes, sir.
See, the changes are happening at the 10th place of decimal of 15th or 12th place of decimal. That decimal place change is like a constant only, no? I'm getting a point.
Yes, sir.
So if you go to a petrol pump and if you look at the meter, the unit place will change very quickly. 1, 2, 3, 4, 5, 6. But the 10th place will change slowly. 1, 2. But the 100th place will change after a long time. So what about the lakhs place? I mean, there is no car which will have that much capacity that you will ever see that counter changing at all, isn't it?
Yes, sir.
Anyway, try to understand this is a statistical law. The validity is only when the dn by n is very, very small. Okay. So this probability, in fact, the lambda is very interesting. Inverse of lambda is called, what? The mean value. The average. The
Yeah.
average is, it's called mean value. Okay, so we'll come to that also. That's very easy to understand. Now this probability is clear.
Yes, sir.
So what is the probability per unit time? Lambda. Okay. So how we derive the formula? You all know the formula. I think it's very simple, pretty simple. So we can say. So what I'm saying is that the probability is proportional to time interval. That's logical. More the time, more the nucleus will disintegrate. Isn't it? As the time will grow, more nucleus will disintegrate because you're giving more time to disintegrate.
Yeah.
So as the time of observation will grow, this will happen. Isn't it?
Yes.
Yes,
That's
sir.
why the dn by n we can write as some constant into time. And now you know how to integrate. So when t is 0, you start with some number of nucleus. Let's call n naught. When t is t, you can call it n. So your answer is known to you. And it will decay exponentially. It will decay exponentially. So if you pull out the graph of n versus t, if you start your observation when the number of nucleus is n naught, it will decay like this. And will become 0 at infinity, maybe some billion of years. Okay. So there are many ways of writing. You can also write as, since dn by n is lambda dt, so you can also write as sometimes dn by dt. This is the rate of disintegration. This is called the rate of disintegration. So the rate of disintegration is how much?
Lambda.
Lambda dn. Sorry, lambda n. What does it mean? A large n will also assure a large disintegration. So as n will grow, dn will grow, so that the ratio remains same, right? That's the whole idea. No? The probability per unit time is constant, which means a large nuclei will decay also in large number. So the
keep the
ratio
ratio
remains same because we want to keep the ratio constant, right? So as more the n, more the dn also. That's logical.
Yes,
Yes
sir.
or no?
Yes,
Yes,
sir.
sir.
I mean, everything is logical. I mean, there is nothing to be mugged up. It's like, it is saying that, okay, if you have large number of n, the dn is bound to be large so that the ratio remains constant. And that's why the rate of disintegration, like how many will disintegrate, depends on the present state of available nucleus. Okay. So the rate of disintegration, of unstable nucleus is proportional to present state of what? Present state of number of remaining nucleus, isn't it? Correct?
Yes, sir.
dn by dt is lambda into n. That's logical. So dn by dt is lambda into n. That's why this term is also called as, what do you call? Activity. How active is the the disintegration process? So the activity depends on how many nucleus or nuclei are available to you. So we call it activity and we represent by symbol A. So activity at any instant is lambda into the number of nucleus at that instant. Is this clear? Activity is clear?
Yes, sir.
And from the radioactive law, because we know this, we know that n equals to n naught. If I multiply both sides with lambda, this is called the present activity. This is called the initial activity when you started your observation, right? So can we say A naught? And this is present activity. So activity will follow the same formula as the answer for n, right? Because anyway, lambda is a logical thing. Lambda, we know what is lambda. See, every nucleus will decay, but no one knows when it will decay, but someone will decay. So we have no control over the particular nucleus. We have control over the general nucleus. Someone will decay. Someone will die. I cannot say you will die or you will die. I can say someone will die because they have very old. So if they are very old, it means they are supposed to disintegrate. Okay. So there's a common question that what is the average life they lived before the decade? Okay. So average life of nucleus. What is the average life of nucleus? See, I cannot talk about the individuals, but you can talk about the cluster. So average means what?
So sum upon total integral TDN upon integral TN.
Correct. So we have n number of nuclei at t equals to 0, let's say, or let's say t equals to t. And then after time dt, we are left with how much? N plus dn. So can I say that dn nuclei lived for at least t time? So these many nuclei lived for how much time?
T.
So I can say the average means what is that dn1 into t1 plus dn2 upon t2 and like so on, with the dot upon what? Oh, sorry.
Upon integral.
Upon dn1
TN.
plus, because we have found the average life, right? Life is average. But because it's a continuous process, how to write this actually in terms of integration, right? So the meaning is these many nuclei lived for t before they decayed. So t minus dn into t is the the DN life of DN nucleus, and if you integrate, you get the for the overall from okay, I'll put the limit later on, and we have to divide by minus DN. This is called the T average. So you can write as T DN by. I mean, there are many ways of writing. Minus DN. What is DN, by the way? So we know DN in terms of what is DN?
Lambda and dt.
DN by dt is lambda n, so minus DN is lambda n
Lambda
dt, right?
Yes.
You can just substitute. So minus DN, okay, just minus DN is lambda n dt and lambda n. So lambda will cancel out because it's constant. So what we are left with? T n dt upon n dt. And what is n, by the way? We know the n in terms of see, n is variable.
And not e raised to minus lambda.
So if you use the integration by parts,
Yes, sir.
and we have to take t from 0 to infinity because they can live from any time from 0 to infinity. Okay. And because we are integrating up to infinity, it means it will not matter that how much time you started with. Okay. So wherever you start, you can get the average value. Okay, because when you start the observation, you can say, okay, they have lived for that time. So the time is anyway not going to contribute to the average calculation. So T average is how much? Tell me. So I hope you can do the integration by parts. You all know the by parts relation, integration by parts.
Yes, sir.
So inverse of lambda is also called the average life. So lambda is representing inverse of average life. It means it is representing the life. I mean, sorry, how small or big the life is. So they are inversely proportional. So sometime in the question, they will not give you lambda, they will give you T average, the average life of nucleus. Okay, so I need to, okay, my page is like ending at 20. So can we continue the next lecture? Because anyway, it will take 1 hour. So we will continue the next lecture. Okay. So next lecture will be some practice. So I'll share the practice notebook. I mean the sheet. Solve it as much as possible, and we can do some doubt and the remaining theory. With
Okay,
this,
sir.
we'll complete the modern physics. We'll start
Yes,
the
sir.
radiation pressure actually, the EM wave. So very soon I'm going to start the EM wave. Again, it will be for everyone.
Yes, sir.
And